Okay. So we're going to start talking about the presentation number 7, which is ARIMA models. Okay. Last time we reviewed ARMA models, and I will introduce the difference in term here to be able to handle more series. Okay. And the ARIMA, the I stands for integrated because it's an autoregressive integrated moving average models. And they are just a generalization of the ARMA models. That the ARMA, to be able to handle what we talked earlier about, which we called polynomial non-stationarity, adaptive polynomial non-stationarity. So when we have non-stationarity due to an adaptive type polynomial, it can be linear, could be quadratic, whatever. The way to deal with those series is to take a difference or take two differences. So what we're going to do is, let's suppose that the underlying polynomial that reflects let's say the trend of the general trend of a series is a polynomial of order 3. Then to be able to make it stationary, that series, we would have to take 3 differences. Okay, so d will be equal to 3. So we'll specify by little d is the number of differences we're going to have to take. Okay, so the original series z tilde, it's already centered. We already centered that series, and we assume that it's non-stationary because of the presence of an adaptive polynomial trend. Then we can build a process. I'm calling it here WT, which is the difference operator raised to the d power if it's a polynomial of order of degree d, applied to the original series, and that series that we call that the dth differences of whatever the difference of order d of zt will now be stationary, at least in terms of the trend. Okay. Now for this new series, the model, if we apply now an ARMA model, see this new series, once we make it stationary, then we can go back to the ARMA models that we saw last class and feed an ARMA model. Okay, so we'll be feeding an ARMA model to WT, which is the difference of order d of the original series. Okay, and that's what we call an ARIMA PDQ model. So in the order, this is standard notation. We'll use P for the autoregressive order. P is the autoregressive order. D is the number of differences, and Q is the moving average order. Okay. So that's a standard notation, and we call that an autoregressive integrated moving average model. Okay, and we'll denote by ARIMA with orders PDQ. That's a standard order in which we specify the orders of the autoregressive, the number of differences, and the polynomial, the order of the moving average polynomial. I forgot to enter with my iPad in case I need to write something. Let me just. Oops, taking too long time to go get into the meeting. Let's see. Okay. Tango. See now, yeah, and that's it. Okay. Now, if I need to write something up, I'm ready. So that's it. That's the ARIMA model. Okay, that's a more general class of models that will be helpful in fitting a wider and a larger number of time series that we find in practice. When we look at the AR models, it's very limited application because they are only applicable to purely autoregressive models. And the same happens with the moving average models. And we make it a little bit flexible, more flexible when we put the two things together, the autoregressive and the moving average. And now we're making it even more flexible to accommodate for non-stationarity, of the type of adaptive polynomial, okay, for their D. Now, why is it called integrated? See, it's called integrated because if you look at the expression we had before, we saw what? We saw that we define WT as the difference of ZT, okay? So if in a sense, what we're doing is we can express ZT. What I'm writing is not correct, okay? What I'm writing is not correct, but anyway, this is the difference operator to minus D, WT. So I'm inverting the difference operator, and the difference operator is equivalent of a derivative. So the inverse of a derivative will be an integral. So that's why we call these things integrated, okay? Because of the equivalence with an integral. That we're integrating over to obtain the ZT back. We're integrating WT to get ZT back. Okay, so if I express the difference operator to the -1, that'll be 1 minus b to the -1. This, of course, would be a sequence that would not converge if I look at the coefficients, right? It would be a divergent sequence. But in essence, this is 1 plus b squared plus b cubed and so on. So we're integrating. So we would have ZT would be WT plus WT minus 1 plus WT minus 2 plus WT minus 3 and so on. So we're expressing ZT as a sum of WT and all its past, okay? All the paths that we have for WT to integrate ZT. That's why we call it integrated. Now, our focus is on stationary and invertible models. That is, we want to make sure that the coefficients related to the autoregressive part are the roots of the autoregressive polynomial lie outside the unit circle, and the roots of the moving average polynomial lie outside the unit circle, so that the models that we'll deal with will be invertible and will be stationary. Okay, that's the type of models. Now, when we fit a model, the algorithm is searching among to find the estimate of the parameters. What the algorithm is doing is it's searching for the roots of these polynomials that make the polynomial invertible. Okay, so when we get the estimates, that model will be stationary. But we need to make sure that before we fit the model, that we are dealing with, we eliminated that polynomial trend of order D. What's the model building process? The first thing we do is identify which type of model, okay? Then we estimate or train the model. Okay? With the data we have, we estimate or train the model. We validate the assumptions of goodness of fit. Remember, the main assumption is that the ATs are white noise. So they are independent with constant variance and approximately normally distributed. So those are the three things that we check. That the variance of the ATs, the white noise, is going to be represented by the residuals of the model once we fit it. So we check the residuals to make sure that the residuals show constant variance, that they are close to normal, okay, and they look independent. And that's why, and the other thing we check with the residuals is the autocorrelation function of the residuals. We are supposed to have residuals that are not correlated. Once we validate the assumptions and the goodness of fit of the model, we implement and use it. Okay, that is implemented and used. So that's the identification process is not a single shot thing. Okay? We identify a tentative model, and then we estimate it, we validate the assumptions, and if the assumptions do not hold, we need to go back to the identification stage and try a different model. So we'll go through the whole thing again. Identify a possible model, do the estimation, then do the validation. And if it's not the right model, if there's a lack of fit, or if there's the assumption of constant variance is violated, or the assumption of independence is violated, then we have to go back to the identification stage. Once we have a model that has gone through the validation, and it's a good model, it's a model that fits well our data and that satisfies the assumptions, then we utilize it. I mean, we use the model. And the other thing that is not drawn here in this diagram is there is a maintenance part. Okay, so when I'm utilizing the model, I have a maintenance stage, because I'm using the model, and the models are not good forever. For example, if you have monthly data, and let's suppose you have sales data, which are monthly data. Well, once you did already, we're now in September, so you have the data until August, up to August, end of August, and then you feed in a model with that data and forecasted September, October, and November. Okay, you forecast 3 months. Well, once September is over, I have the data from September. So what makes sense is to update the model. So I need to go back to the estimation, okay, stage with the data that are just arrived from September. I still have to validate and then put it in production. Okay. So data and models need to be maintained. They are not static. Now, there's type of models that are used for streaming data that are coming as a stream. Well, those type of models, they are updated continuously, and the process changes a little bit, because with those type of models, the validation is only periodic. Okay, so for example, if you have data from a sensor that's you're in the manufacturing environment, you have sensor data from a sensor, or that's measuring temperature or oil viscosity and so on. And you forecast what the next the temperature is going to be the next period of 8 hours, which is the next shift. And then every time you have more readings of the temperature, the model needs to get updated automatically. Okay, those are different types of models. But you still go through the stages the first time, and then once in a while, let's say every 6 months, or everything that there's a reason to believe that something changed. For example, I changed the supplier. If I change the supplier for the oil, for example, then I need to review my model and make sure that the model that I identified before is still a good model. Okay, so there's a maintenance stage that's not here, but that's part of what having a model in production means. Now, the identification part is very important, and what we want to achieve in the identification part is essentially determine the orders of the polynomials P and Q, the orders of the autoregressive part and the moving average part. But also, and more important than that, we need to identify how many differences we need to take to make the series stationary. Okay, so in the identification, we want to identify which is the right number of differences first, and then once we have identified the number of differences, then we identify the orders of the autoregressive and the moving average part. Now, before we determine the number of differences, we need to make sure that the variance is constant. So the first stage in model identification will always be graph the data, and if there is an indication that the variance is not constant, you need to correct that before you identify the number of differences and try to identify the orders of the autoregressive and moving average polynomials. So the first thing is always check your plot of the data to make sure that you have constant variance. Now, if
we don't have, I was going to ask this, like if we don't have constant variance, like Boxcox,
yeah,
it's already there.
Yeah, if you don't have constant variance, what we do is we use the Boxcox family of transformations to stabilize variance. Okay, this Boxcox family of transformations, if you already took regression analysis, you also have seen this Boxcox transformation. And the way to determine lambda, here the parameter we want to determine is lambda. Okay, and the way to determine lambda in regression analysis, where we have independent observations, we don't have correlation with time, is different. The way to determine lambda in regression analysis is through maximum likelihood. Whereas here in time series analysis, we want to have variance to be constant over time. Okay, so what we're going to use is we're going to do is want to determine lambda that will make sure that over time I have constant variance. Okay, that's what we're going to do. So the method is to choose lambda so that the coefficient of variation, that the sigma, that is the standard deviation divided by the mean to the 1 minus lambda, is constant for different periods of time. In essence, what we want to, we do not know sigma, and we don't know mu either. Okay, so but we can estimate sigma, we can estimate mu, and what we do, so this is what we want to achieve to get lambda, the lambda that makes this thing constant for all t. Okay, so if you have notice that sigma has a subindex t is the standard deviation at time t, and this is the mean at time t. I'm assuming here that we may have different means and different standard deviations at different periods of time. So what we want to make sure is that the ratio of the standard deviation to the mean remains constant regardless of time t. But we do not know sigma, and we do not know mu. So the procedure, let me put. I'm going to go for a blank page. Let's see. I'm going to work here. The procedure that essentially what we do, and I'm going to draw a series here. Is suppose that my series looks like this. And I look at the graph. I'm going to make it. So here's a case where I do not have constant variance, right? My variance appears to be increasing. So the method used in time series to choose lambda, what it essentially does is it splits the data in contiguous regions, okay? So I split the data, and depending on if I have monthly data, I may choose periods of 12 months or whatever. The algorithm takes care of that, but essentially what's happening in the algorithm, so you know what's happening in the algorithm is the following. The algorithm essentially is splitting the series and say in chunks. Chunks about the same size. Okay. Then for each of these chunks of the series, I have an estimate of the variance that is the spread, right? I have an estimate of the variance here, an estimate of the variance here, an estimate of the variance here, an estimate of the variance, and so on. Then what the algorithm does is it takes lambda, it takes the transformation, it transforms the series, and does the same thing again, takes the same partition and computes and see if the variance now is constant. And we'll end up with a lambda that makes this look like constant along the time axis. That's the algorithm. And that is different than what happens in regression analysis, because Box-Cox transformation is also used to approach normality, to when we have data that needs to be to approach a normal distribution. Okay. Now the transformation, as you can see here, is zt to the lambda. So for the lambda that we select, is z to the lambda for lambda different from 0. And if lambda is equal to 0, if the lambda that makes that variance constant is equal to 0, then the transformation is the logarithm, the natural log of the original series. Okay. Now let's look at this Boston armed robberies series. We have seen this series before, and when we first saw this series, we noticed that there seems to be an increase in variance. Okay, so it looks like the variance is increasing with this in this series. So that before we identify the model, we need to make sure that we make that variance constant. So this is the original series, and this is the transform series. So here, we're going to go over the script now, but the lambda that was selected by the algorithm was very close to 0. So if the lambda you choose is very close to 0, then it makes sense to take the logarithm, okay? Because particularly in cases like this, it is clear that you have a polynomial trend of order 1 in this series, okay? You have a polynomial trend of order 1. So the most likely thing is that you're going to end up taking a difference. So taking the logarithm of the series makes sense, because when we take the difference of the logarithms, we're looking essentially at the increases or decreases in robberies from one period to the next. Okay, we're looking at the rate of increase or decrease of the robberies. So if the lambda is close to 0, we choose the logarithm, because it's easier also to explain. Now, lambda normally is selected in a range between -2 to 2. But if we get a lambda, the algorithm can be very flexible. You can select lambdas even to -4 to 4. There are some values of lambda that do not make sense from a practical perspective. Okay, for example, if I get a lambda that lambda is 2, I'm just squaring the data, and unless that has a physical explanation, the subject matter expert says that it makes sense to work with the square root of the original data, then we would make the transformation. Otherwise, sometimes it's better not to transform, and we'll go over the different cases here. But if you get a lambda that's very crazy, like 4, something greater than 2, greater than or equal to 2, that lambda usually is too large, unless there is an explanation. Okay, and there is a subject matter expertise that indicates that the second power of the data, it makes sense, or the square root of the power. For example, the square root of the power, in many cases, it makes sense. Okay, but taking the series to the -2, if it doesn't make sense from an expertise type point of view, unless the variance is definitely really weird, we should consider if we take a power of -2, for example, if there is no explanation for that. We'll normally end up with lambdas either close to 0, in which case we would go with the logarithm, or square root lambda equals to either 1/2 or minus 1/2. This is the once we stabilize the series. So here we already stabilize the series in the sense that we do not have constant. We do have constant variance now. Okay, we do not appreciate the same pattern, funnel pattern that we see in the original series, where I can see the increasing variance there. Once we stabilize it, then we work with this series to identify the model. So we're going to be working with the logarithm of series. Once we transform the data, then everything we do after that point to fit the model, to identify the model and to fit it is going to be working with the transformed series. Okay. So once we have the transform series, that's the one we start analyzing to identify the model. Now, what the next thing is to do is to determine the number of differences. From the plot of the data, it was clear that we still have a trend. So it's very likely that we need to have one difference. If we look at the ACF of the logarithm of robberies, the ACF dies very slowly. This indicates that we do not have stationarity. Okay, so I need to look at one difference. And I have here the difference of the log of the robberies, and that's the ACF. Now the ACF looks a lot, essentially we have one significant lag in the ACF, which is lag 1, okay? And the rest is noise. The rest is noise. So it looks like if I just look at the ACF, the autocorrelation function, it looks like if I work with the logarithm of the robberies, that the model could be, just looking at this, I haven't looked at the partial autocorrelation, but from here we would say it's probably an ARIMA. An ARIMA, why? Because I have to take one difference of orders 0, 1, 1. Why? Because I have one autocorrelation that's significant, the rest are negligible, the rest are 0, and that could be an MA model. Okay. Although we haven't analyzed yet the PACF, the partial correlation function. Okay, so this will be the model, but this will be the model for WT, which is the log of CT. So we start working with the log, and we feed the model to the log data. Okay. Now, remember that we said that if you difference a series that is stationary, you get another stationary series. Okay, so you can keep taking differences, and the series will still be stationary. Now, if we over difference, that makes the process of identification and estimation more complicated. Okay, so we need to make sure that we do not over difference. So how do we check if we do not over difference? Well, one way is looking at the ACF. When we saw the ACF for the first difference, we saw that already dies right away. So there's no reason to go for another difference there, because that, unless if I saw that the ACF was not dying fast enough for the first difference, then I would go for the second difference. But it's always good to check if I take a second difference, what happens. So the way to check if we over difference is to check the variance or the standard deviation of the original series, the first difference, and the second difference, for example. And if I take a second difference and the variance increases, then that means I am over differencing, and I need to stick to one difference only. Okay, so this is for example, for the log of the series, the log of the robberies, that's the standard deviation, 0.78. Then the standard deviation for the log of the for the first difference of the log of the series is 0.207. So there's a big decrease. But then if I take a second difference, the standard deviation increases, okay? It goes from 0.20 to 0.32. So that means that D is equal to 1. So this tells me that D is equal to 1. Because if I take a D equal to 2 differences, my variance increases. So I am over differencing already there. Okay. Now the bars that we saw, we've already talked about those, and the ACF are like the confidence bands, assuming that the autocorrelation for each of the lags is equal to 0. That will be under the hypothesis that that's equal to 0, that will be a 95% confidence band. So the criteria to see how many of those ACFs, of those autocorrelations, are significantly different from 0 is if they are outside the bands. Okay. Now the calculation of this interval, if this 95% confidence interval, is based on a result by Bartlett, which essentially what it does, assuming that the process is generated by white noise, then the variance of the kth autocorrelation is approximately equal to the same. Okay, and the variance and the covariance between RK and RK plus S for any value of S is going to be approximately equal to 1 over n times the sum of rho j and rho j plus S. Now, of course, we do not know rho. Okay, so we use the estimates. So we don't know rho. Okay, but that's the approximation that's used to compute those confidence limits. That's the approximation that's used there. If the process is an MA, then the approximation for the variance is given by this approximation is 1 over n minus d plus 1 plus 2 times the sum of rho j's squared. Okay, so that's those are the formulas that are used in the different packages, statistical packages, to compute those confidence bands. Okay, and as you can see, that was that was in 1946. So that hasn't changed. The theory is still valid, but now it's very easy to get these computations done. Okay. So this is the estimated variance of RK under the hypothesis that the correlation of or the K for K greater than Q. Okay, so what I told you earlier, the rho J's, we do not know the autocorrelations. Okay, so we replace them by their estimates. Okay, and these are good estimates if we have at least 50 data points. Okay. So that's an important restriction. These type of models, if we have, for example, monthly data, that means that we need at least 4 years of data, right? If we have monthly data. If you have only 1 year of data, these models are not going to be useful because, first of all, you may not be able to even estimate the model if you have to take a difference, for example. Because you have 12 observations, and if you take a difference, you lose 1. So you would end up with 11 observations only. So we want to work with larger data sets, and the number of data points in the time series should be at least 50. Now, there's covariance among the autocorrelations. We saw it here. There is covariance among the autocorrelations. Okay, there exists covariance. They're not independent. So the ACF will show a pattern caused by such covariance. Okay? If we didn't have covariance, then we wouldn't have to see a pattern. But since there is covariance, we will see a pattern in the autocorrelations. Okay. Now, the bands for the ACF represent the confidence interval for the sample autocorrelation under the hypothesis that rho k is equal to 0. Okay. So for each value of k, if under the hypothesis that the autocorrelation of lag k is 0, that's the way you compute the confidence intervals. Okay. Now we saw already when we talked about the ARMA models that looking at only the autoregressive, the ACF, the autocorrelation function, if we have a purely purely moving average model, then the ACF is good enough to be able to identify the model. We don't need more. Now, we never know if what we have is an ARMA model or MA or an AR. That's what we have to determine. So we need to look at the PACF, the partial autocorrelation function, together with the ACF. Okay, and that script that we reviewed last class, the good thing that script has is that you can generate several series, and you can generate the theoretical and the estimated ACFs and PACFs. This is the ACF of an AR1. This is the ACF of an AR2. So just looking at the ACFs would be very difficult to determine if it's an autoregressive model of order 1 or order 2. Now we know that if we look at the PACF, the partial autocorrelation, then if it's an AR1, the first lag would be different from 0, and the rest will be 0. And if it's an AR2, the first lags will be different from 0, and the rest will be 0. Okay. When we have ARMA models, the behavior looks like this. For an ARP, we already see when we studied the AR models by themselves, we saw that the function, the autocorrelation function, converges to 0. Okay, and the behavior of that convergence is given by the autoregressive equation. Okay, by the autoregressive polynomial applied to the autocorrelations rho sub k. And the partial autocorrelation function, it only has 1 or 2, the p significant lags. Okay, only the first p partial autocorrelations are different from 0 in the PACF. Okay, now here, let me just make sure this. Now for an MA, we already saw that only the first Q autocorrelations are different from 0. And the PACF is an infinite succession that converges to 0. Okay, so that's a clear indication when something is an AR, a purely AR model or pure MA model. In an ARMA PQ, we have irregular behavior during the first Q autocorrelations. So if you look at the ACF, the behavior for ARMA PQ will be irregular for the first Q autocorrelations. And then we'll see convergence to 0 according to the autoregressive polynomial. Okay, so the first Q will be regular behavior for the ACF, and then after lag Q, after the convergence to 0, after that, at the first Q lags, there will be convergence to 0, and the convergence will be dictated by the autoregressive polynomial. But we'll see a pattern similar to what we see in the ACF of an ARP here. Okay, and the PACF will be an infinite succession converging to 0. Okay, now what will help me determine Q and P will be to look at both charts, the ACF and the PACF. Now, the admissible region, that's the region where the parameter values satisfy the conditions of invertibility and stationarity. That's what's called the admissible region. And the algorithm will estimate parameters that are within that admissible region. So for an AR1, we already saw that the admissible region is the interval between -1 and 1, excluding the ends, okay? It's an open interval between -1 and 1. For an MA, for an AR2, we saw that the admissible region was determined by this set of equations: phi2 minus phi1 less than 1, phi2 plus phi1 less than 1, and phi2 between -1 and 1. Okay. Now, this for an AR, for an AR2, this admissible region will be represented by this region here, okay, by this triangle, and what this curve is doing is dividing the values for the parameters according to whether they correspond to real or complex roots of the characteristic polynomial. Okay, that's admissible region. And the algorithms that are implemented in all the software packages are looking for estimates of parameters within the admissible region. Okay. Now, I took these pictures from a book by Victor Guerrero, and these are this tells you for each of the models what's the ACF and the PACF. This is the theoretical ACF and theoretical PACF, and these are data generated from this model with phi equal to 0.5, and the PACF, the sample partial autocorrelation. Okay, so you can see the behavior. Again, these pictures are okay, but they may not be that clear. But if you can generate all these models with the script that I gave you, that you already have and we used last class, to generate different models and see how the ACF and the PACF, both the theoretical ACF and PACF and the sample ACF and PACF, look like for different models. So there's several pages here. That's just for your reference. If you can achieve the same thing, all these models you can generate with that script and have much better pictures of the different types of behaviors. Okay, so I'll just leave this thing for you. But this is something that you can refer to if you haven't run the script with different models. This is something that you can refer to and look at patterns of behavior of the ACFs and PACFs, and try to identify if it's an AR model, an MA model, or an ARMA model, in the type of order of the ARMA model. Okay, that's it. Now let's go back to the armed robberies data. This is the ACF. We saw a significant lag here, and then the PACF has essentially two significant lags apparently there. Okay, so this could be what we mentioned earlier, an ARMA 1001. Okay, one moving average term because of this significant ACF here. This could lead you to believe that maybe it's an AR model of order 2, but there's no pattern. If you look here, these two are significant. There's no clear pattern here, and there's no clear pattern here. So it could be either one, and we'll see that the same series can be represented equally well or almost equally well by two different models. And we'll always look for the one that's more parsimonious. So here, this is a fit of the ARIMA 111 with the log of the series. That's the ARIMA 111. And it turns out that the three parameters are significant. That's the autoregressive coefficient, the moving average coefficient, and the constant term. All of them are significant. We took one difference, and we're working with the difference of the log of the robberies. Now, remember, the residuals are estimating the ATs, the white noise. So what do we check from the residuals? Well, we check that they behave normally. I mean, they behave randomly, okay? And I can check just the graph to see if there's no pattern here. I would also want to check here if I have a constant variance, okay? That we need to have constant variance in the residuals. If we do not, that means that we need to go back to the identification stage and transform the data, okay? If we do not have constant variance in the residuals. Because maybe that lack of constant variance, we didn't perceive it in the original plot of the data, but it's noticeable in the residuals. So we will need to transform the data. We need to check if they are close to normal. So that's the normal probability plot. Okay. And this is the autocorrelation function of the residuals to make sure that they are not autocorrelated. They should be, the ATs are independent, so I should not have autocorrelation between in the residuals. Okay. Now I'm going to go over these AMP robberies here, and with the R script. There you have the R script in. Let's see, scripts. It's called ST07. Modelos ARIMA. Okay. Just download that script number 7 to your computers, and we'll use the data. You already have, you must have already the data set of Boston armed robberies in your labs or in your desktops, because we already used this series. Okay, but just install the packages and run over line 27, who we plot the data. So we saw earlier that there's a clear pattern here that shows that the variance is not constant. So we need to transform the data first. That's the first step. So I compute lambda. I use the function boxcox.lambda. This gives me the optimal value of lambda to make the variance constant. And if you see here, but lambda is 0.31. So it's very close to 0. So I would be inclined to choose the log. Now, to make sure that I can use the log, I'll first look at the plot. I'll transform it using the lambda, the optimal lambda. Okay, if I choose the Box-Cox function, transforms the series using this lambda. The optimal, in this case, will be the optimal lambda. So I take T robberies, and that's the Box-Cox transformation, and I plot both, and I see that, yeah, the variance seems to have been stabilized in this thing. Now, since lambda is close to 0, I need to try to see if the log gives me good enough results. So I look at I compute the log of the robberies, and then I plot the robberies and the log of the robberies. So I'm taking the log, I'm taking Box-Cox, and then using 0. I could just take directly the logarithm, the natural logarithm of the robberies. Now I plot both, and if you look at the two charts, at this one and the previous one, this is with the log, and the previous one is with the optimal lambda, and there's practically no difference between the two charts. Okay, there's no visible difference there. Okay, and so it makes sense to work with the logarithm instead of the raising the value, the series to the 0.3 power. It makes the sense different working with logarithms because we know we have to take a difference here. So let's look at the ACF of the log of robberies. ACF, this function ACF2 gives us the ACF and the PACF. And that's from the ASTSA package. Okay, this comes from the ASTS. This ACF2 comes from the ASTSA package. And now I'm going to plot the difference of the log of the robberies. Okay, well, already saw that plot. I'm going to omit this one here. But this is the ACF2 of the log of the robberies, and I can see that when I take one difference, now the series seems to be stationary. Now, one thing that to notice here is the value of the autocorrelation. This is the ACF that dies very slowly, and this is the PACF. Okay, notice that this value is very close to 1. And this is dying very slowly, okay? It looks like if I identify the AR1 model here without the difference, then the parameter will be very close to 1, which is equivalent to taking one difference. Okay? Now, definitely we need to difference the series because of it's dying very slowly. The ACF is dying very slowly. So we look now at the difference of the log of the series. And we can see what we observed earlier. We observed that I have significant lags here and here. So if I only looked at this one, if I only looked at the ACF, which is what we talked about in the class when we just showed the ACF of the series and the first difference, I could think that it's an NA model, but this is telling me that I may have AR terms also, okay, because I have 2 lags that are significant. So I may have an AR term, at least one AR term. So I'm here, and okay. Now I'm looking at I'm going to put the 3 series together. If I look at all I'm showing here is that here I'm losing 1 value and here I'm losing 2 when I take the second difference, okay? So I want to check if I need to take a second difference. So I put all this together. Now this is the first difference and so on. And I included this function here because if I want to look at the 3 standard deviations, I can use the function apply. I put all the series in a single data frame first. So I did a cbind, que es column bind of the log of the series, the difference of the log of the series, and the second difference of the log of the series. So I have the 3 series in the data frame. And now what I want to do is I want to compute the standard deviation for each. But if I define this function to make sure that I include the option, the parameter here that they remove NA values, because I have an A value here. If I just apply, we had seen this function before, right? If I just say apply with the standard deviation function, it will give me NAs here. It will not give me a standard deviation because I need to make sure that it removes the missing values. So that's why I define this function here. There's stand, and all it does is I define a function of x, which is essentially the standard deviation of x with the parameter NARM, remove missing values equal true. And then I can do the apply now, which I remember apply works with rows or with columns. So I'm applying this function to the columns of this data frame. Okay. So I apply the function to the columns, that's a 2. If I wanted to apply a function to the rows, I would use a 1 of this data frame. So I can see that the variance, the standard deviation increased. So I need to stop at 1 difference. So I'm gonna, let's assume that we thought that since we have 2 significant lags here, we thought that could be 2 AR terms. Okay, so I'm gonna start feeding an AR211. So I feed, I use the function SARIMA. SARIMA is also from the package. This is from the ASTA package. ASTSA package. And it has the advantage that it gives me the diagnostics at the same time that it fits the model. So model 1, I called it like that. So if you look at the model, the second autoregressive term is not significant. Okay, is the p-value is very large. So what this means is that if I were to test the hypothesis that phi2 is equal to 0 against the alternative that it is different from 0, I would not be able to reject the hypothesis that phi2 is equal to 0. So what I do is now remove phi2, the second autoregressive parameter, and I feed the model with only 1 autoregressive term. Okay. Now my 3 parameters are significant, are statistically significant, different from 0. And what I see here is, if checking my diagnostics, my residuals look to be a constant variance. They have a constant variance. They have a spike here that's large, but that's just an observation. But we have constant variance. We have a random behavior. We don't see a pattern. For example, what type of things do we look at? If I were to look at to see a pattern like this, a sine wave pattern, then I would have to get worried and do something. This means that I still have autocorrelation so I need to add. If I saw a pattern like this, what that would be indicating is that I need to add autoregressive terms. Okay, if I see something like this, if I were to see variance decreasing, increasing, or decreasing, well, that's an indication that I need to go back. If I saw something like that, right? Some funnel type pattern, that will tell me that I need to go back to transformation. So that they look random, and that's confirmed by the autocorrelation function of the residuals. The normal probability plot of the residuals looks also reasonable. Okay, they're pretty close to a normal to the straight line, so there's no indication of lack of normality. And then this Young box statistic, we haven't said what this thing is, but essentially what this Box-Young statistic tests is, then at each stage is testing. For example, if I take this one here, these are p-values. This is the p-value for which test? This is the p-value for the test that says that the null hypothesis that rho k equal to 0 for k less than or equal to 5 in this case, versus the alternative that rho k is different from 0 for at least 1 k between 1 and 5. Okay, that's a hypothesis that's testing. So since this p-value is very large, I do not have evidence to reject the null hypothesis that the autocorrelation, the first 5 autocorrelations are 0. So this, for example, here is testing this is lag 10. So it's testing that the first 10 autocorrelations are different from, are equal to 0, against the alternative that at least some are equal to 0, are different from 0, sorry. Okay, so that's what that Young box statistic does, and it's very useful statistic because what we want to see is things like this. We want to see p-values that are large because those are indication that I have a good fit of the model, and my assumption of white noise that it's made at the beginning to develop the estimation of the model, that assumption is a valid assumption. So there's no reason to doubt that assumption. Okay. So now what I'm going to ask you to do is nothing because it's almost 20 minutes to 10. So we'll stop here. Are there any